Well, so I'm the chair of PPDP, so there are some people from PPDP okay, that came. Oh, yes, it's true. No, well, but in PPDP, it's very loud. Well, in PPDP, we are doing this thing, okay? So we take the microphone, okay? People in LOPSTR, you will get used, okay? So remember that you have to speak to the microphone all the time. So it's my, sorry for the joke. So welcome, okay? So people of LOPSTR, so PPDP and LOPSTR have been together for many years, okay? So it's a very nice common community, okay? So welcome people in LOPSTR, okay? And those of PPDP that came here, okay? So you can stay for the rest of the session, okay? And then we will have more stuff, okay, after lunch, okay? And, well, it is my pleasure, okay, to have Maribel Fernandez here as invited speaker, okay? So she's an expert in so many things, okay? And I met her many years ago. I'm so happy to have her here, okay? But I think that this topic, okay, that is not showing, but that we will...
Is it possible to switch?
No, but it's okay, yeah, but this topic is a very interesting one, okay? Binding operators in general, okay, and all the nominal effort that she has been doing for years, okay? And I think that it is a very important effort, okay, and a very interesting talk. So, thank you, whenever you want.
Thank you, Santiago, for the introduction, and I'd like to start by thanking the chairs and the program committees for both conferences, which are conferences I really feel part of these communities. I've been attending them for many years, and so I'm really very happy to be here giving this talk, and also in this very beautiful place. And I want to also give a special thanks to ALP, which is the Association for Logic Programming, and they are sponsoring my talk here. So like Santiago was saying, this is, we are discussing in this talk an approach to specification of problems, specification of systems, where some of the operators in the system are what we call binders. And what I'm going to describe in this talk is part of an effort from a lot of people, so it's like a teamwork. My collaborators for this particular topic that I'm going to discuss today in nominal techniques come from different areas in the world. So some are in Brasilia, like Daniele and Gabriel and Ana Rocha, and some in Washington, some in the UK. Some are my PhD students, and also Andy Pitts and Jamie Gabay, who were the proposers of the nominal approach for binding. So without all of them, I wouldn't be able to tell you these things now. So let me just briefly give you an overview of what we would like to discuss today, to cover today. So first of all, the idea of languages with binders. I think this is something that everybody is aware, but there are different ways of seeing it, so just we will agree on what we call a system with binder, a language with binder. Then I would like to introduce nominal logic, which is the basis for the approach we use, and then discuss the main topic, really, of this talk, which is how do we work with these expressions that have binders, and in particular, how can we check equivalences, and then more than that, solve, for example, equations between terms that might have these binders. So the popular notion of unification, which is at the center of logic programming, but also very useful in the area of functional programming. Although we use matching rather than unification to compute, we still want to use unification to analyze properties of functional languages. And in particular, within rewriting systems, if you define your functions with rewrite rules, unification is the key concept for example, to compute critical pairs, to understand overlaps in definitions. So we will talk about unification, and also, in particular, unification in systems which arise often when we are doing equational reasoning. We often have operators that have some properties, so we work modulo axioms. We say modulo, for example, modulo commutativity, modulo associativity and commutativity. So typically, processes in the pi calculus or in other concurrent systems, they are defined using operators like parallel composition, which have these additional properties like associativity and commutativity. So we also want to look at how these things combine, the notion of binder and the notion of an equational theory. Okay, so these are the main papers that I've used to prepare this talk. You see that they range over many years. Andy Pitts introduced nominal logic in 2003, and we had a paper just this year looking at nominal AC matching. So it's a long-term effort. Let me give first a couple of examples, just as I say, to set the context so that we know what we are talking about. When I say a binder, what I mean is the kind of thing that you find, for example, in languages like the ML family that have a let, or Haskell that have a let. Okay, let is a binder. In the lambda calculus, which I guess is the most familiar system for many people, the lambda is a binder. I mentioned before the pi calculus. The pi calculus also has a binder called nu, and this probably is the most basic, is the one that I usually, when I give this kind of talk, and there are students, undergraduate students in particular, that's my favorite one, because it's the one that everybody has seen. For all existential, we know they are binders in first order logic. Okay, but what does it really mean that they are binders? Because this is kind of usually presented in an informal way. So you might introduce first order logic to your first year students and just tell them, pay attention, for all an existential is a binder. It means you can rename the variable. But as I say, that's kind of an intuitive way of saying it. And here we would like to be able to formally define this notion of binder, so that then we can also reason with these systems. We can prove properties. So the intuitive notion, as I said, is that you rename. However, it's a bit tricky because you need to rename avoiding capture, etc. So if you want to really define it formally, I say it's quite tricky, and it's, for example, many of the definitions, even original well-known papers like Church's definition for the lambda calculus had some problems in the definition of the alpha-equivalence relation. It's a tricky relation to define, this relation of changing names. So we can implement it in a first-order system, in any programming language, basically. If you need to do this in C or in any programming language, you can implement this renaming as an encoding. In your syntax, you encode your expressions and you hard code these renamings. You might decide, for example, to represent your variables with indices. So instead of for all x greater than 0, it will look something a bit odd with these indices, but it can be done. And if you do that, if you move down to the really plain encoding, things are okay, they work well. You can do easily comparisons. For example, you can compare if two expressions are the same quite easily because you use the same, supposedly the same indices. So it's matching and unification is easy and efficient, but you pay a price, which is, well, first the effort, because encodings are usually heavy, and second, it's not so easy to then understand what you've got. Okay, when you see an encoded expression, it's not really so easy to understand it. And if you want this to reason with the system, is not great. And also, okay, the last point, there are no meta-variables in your encoding. So it works well if you have the full expression, you encode it. But what if you have an expression where some parts you don't really know yet? Maybe this is, I don't know, a process, an expression in the bicalculus where you have defined some part of it, but your collaborator is working on another part of that process expression. And so what you have is one part is defined, the other part is a big X. Okay, something will come there. So that makes these encodings very tricky. And that's what I mean by no meta-variables. There is a much more elegant, more abstract approach, which uses, is what is usually called the higher order approach. So what you do there is that you choose a meta-language that already has a formal notion of a binder. Okay, so for example, what we call higher order rewriting systems, which are various versions. For example, CLOP introduced combinatory reduction systems, and in the meta-language, there is the lambda calculus. Okay, so you assume already, you know what a binder is, lambda, you know the properties of that lambda calculus, and then you can define things, other things, using that. So clearly, it's very easy to define the lambda calculus in that system because it's already part of your infrastructure, but you can also define, obviously, if you want to define other things like processes, or you want to define first-order logic formulas, and then you want to define a rule to simplify them, or to put them in pre-next normal form, or to do that sort of thing. So that's quite easy compared with the version where you have to encode everything. So there are, say, various approaches, various frameworks that follow this approach of representing systems with binders using a formalism that already has binders in them. So it's elegant, is easier to work with it, perhaps, but you need to be a bit careful, because if your framework is quite powerful, for example, if it already has the lambda calculus in it, then if you are interested, for example, on checking for equivalences or unifying your expressions, you are doing it modulo those things you have in the framework, and unification modulo beta is not decidable. Okay? So you need to restrict yourself to fragments where things work well, which there are fragments, like, for example, the one defined by Dale Miller. So what we propose here with the nominal approach is a different, if you want something more in the middle, okay? What we really want is alpha, the alpha-equivalence relation. That's what binding means. We don't want beta. We don't want to have to encode everything. So we want something in the middle that covers just alpha. And the key idea that Gabay and Pitts proposed is to, rather than move to the theory of functions with the lambda calculus, is to stay in set theory, plain set theory, except they chose a particular set theory, which was called nominal set theory, which includes the notion of a name. Okay? In sets, you can have names. And with names comes this interesting concept of swapping. You can swap names. So their names, their nominal sets are sets with names and with a permutation action on the names defined by the swappings. So based on that, it's possible to define a notion of abstraction. So to define equivalence classes that represent the alpha-equivalence relation. So let me tell you a little bit more concretely. Nominal logic is a theory in first-order logic that uses these concepts I was just telling you. So let's assume we have names and we have a possibility of swapping names. What does it mean? It means that I have some variables in my logic that I consider them to be names or name sorts. It's a sorted logic. So I have variables of sort name, the A's and A primes there have sort name. And these axioms tell me how this swapping works. Okay, so we axiomatize swapping. So the swapping can act on names, it can act on terms, like I can swap A and A prime on a term f of x, or on a predicate, or I can define this abstraction syntax. For the moment, it's just syntax with the brackets. If I move from here, I'm not going to be in the microphone. Okay, here, those brackets. So for the moment, just syntax, but we will also have axioms to define what those brackets are in a minute. So here, those F axioms are, you don't need to read all these. I'm just is to give you the idea that this is a formal theory in first order logic that axiomatizes the notion of swapping names, the notion of a name being fresh for a term. So the F axioms tell you when a name is fresh in a term. Fresh meaning it's not free there. And then what else you've got? These axioms. They are the ones that define these square brackets that I told you is just syntax. It's only syntax. This is first order logic. But because of these axioms, we can understand these brackets as abstractions. So the first one, for example, tells you when two abstractions are equal. Basically, they are equal either because they have the same abstracted name and they are equal, okay, identical, or if they have different abstracted names, it's because if you swap the names, you get the same thing, okay? So it's a way of defining the notion of alpha in a formal way, just using first order logic. And based on that, we can then define languages with binders. So we have the syntax I just mentioned, first order terms, where if I want something to be a binder, I will use the abstraction with the brackets. Obviously, the substitution I have there is just the first order substitution. The variables are first order variables, so it's not a fancy notion of substitution. It's just replacing, it's like grafting, except that, you can do swappings, permute names. But this is fortunate that because this way of formalizing the binder only addresses the alpha relation, there's nothing else there. There's no beta, there's no extra things. We can, so Pitts and Gabay and Urban showed that unification is decidable. Not only that, it's also unitary. So like first order unification, like the one in Prologue, you have one most general solution when things are unifiable. So concretely, the syntax we use. So what we are going to use in the rest of the presentation is where we want to talk about variables. These are like the first order variables, okay? We use capital letters. When we want to talk about names, we call them sometimes atoms, we use little letters, lowercase letters. Function symbols are like in first order logic. We use them to build expressions. And we use these square brackets for abstraction. It's always abstraction of a name and a term. And we allow ourselves to suspend permutations on variables, okay? So if you come from the higher order abstract syntax world, you would probably call those meta variables, not variables. Or if you just don't care about this and you work on the lambda calculus, when you write, lambda x m to define the beta rule, for example, lambda x m, the x is the name you want to abstract with the lambda, and the m represents the body of the abstraction. It's a meta variable, you could say, or in our case, it is a variable, okay? We don't have meta variables, we just have variables, like in first order logic, and some of them are names, and we put them with little lowercase letters. And the idea is that permutations can suspend on the variables. Why? Because the variables represent parts of the expression that you don't know yet. So if there is a swapping that you're trying to do, some permutation of names you're trying to do, that needs to wait until you know what that x is. Okay? That's why the permutation suspends on x. So pi is simply a permutation, really changing names. Okay? Bijection, finite bijection on names. It could be empty, of course. When it's empty, we don't write it. We just put x. And you can use this syntax to represent, for example, the syntax of ML, using just terms. So these are abstract syntax trees, you see. There's nothing more in them, just trees. So if you want to represent an abstraction, lambda a t, when you write lam, that's your root, and then abstract a t. Okay, so it's really the syntax that you would put in Prolog. Okay, it's just first order syntax. But so you can define, for example, the let rec in ML, which binds the f, the function, the recursive function you're defining, and the argument a. And of course, you can sugar that, so you can use the normal syntax, but it corresponds to the abstract syntax you have there, to the trees you have there. And then we have, on that plain syntax, we have, like I mentioned before, there's an axiomatization of the alpha-equivalence relation, which is straightforward. If you forget the one about the variables, okay? So if you have a ground term, a ground expression, let's say a lambda term, okay? It's not lambda xm, it's lambda xx or lambda xy or whatever. So you can check the equality of those two expressions by using these rules here. The tricky one is when there are parts you don't know in your expressions. In that case, you can only say that those things are equal if the suspended permutations that you might have on these unknown expressions do not affect x, which is what this ds pi prime means. The different set of the permutations, the places where the permutations give different results, cannot appear in x. Okay, so that's the only, perhaps, non-standard rule you have to come up with if you want to axiomatize alpha here. So, for example, using this, we can derive the formula there. We know that abx is equal to x, provided that a and b are fresh in x. Or you can know that lambda ax is equal to lambda b abx, provided that b is fresh in x. So there is one more thing that I should have highlighted, which is the rules for abstraction. Okay, the rules for abstractions are these axioms I explained before that say as is equal to it because they have the same abstracted name. It's just sufficient that s and t are equal. But if you have two different names, a and b, you will need to check that s is equal to the result of swapping a and b in t. So basically, you translate them both to an abstraction in a. But it's important that a is fresh in t, because if t has the name a free, these two things will never be equal, since s has abstracted a. Okay? So that's why we have this condition a fresh for t, and that means we need to also axiomatize the freshness conditions, which corresponds to the axioms in nominal logic I showed you before. This just is an inductive definition of when something is fresh. So note, for example, that a is fresh in the abstraction of a in s. Again, the only rule that might be slightly, I think if I asked you all to do it, you would do this directly. Perhaps the only one that needs a little bit of thinking is the one for the variable. When is a fresh in pi x? Well, I need to check pi minus 1 of a. That needs to be fresh for x. So we can derive, again, freshness things that we need for these things using those rules. So you see that we derive alpha equivalences under assumptions of freshness for variables. Okay? We can derive lambda ax equal to lambda b abx under the assumption that b is fresh for x. So freshness assumptions are important in this system. And so with these notions we have now, we can, for example, define term transformations, rewriting. So nominal rewriting is rewriting with these expressions. You can define equational theories, you can do algebraic specifications, define operational semantics of programs or processes. And this is an example where we use nominal rewriting to define the pre-next normal form of a first-order logic formula. So these rules work on the expressions I just defined, where the brackets are defining abstractions. It means that the rewriting relation is working modulo the alpha equivalence relation. So the first rule, for example, can apply to some expression P. This is using infix notation, okay? The conjunction and appears in fix. But if you look at the top rule, P and an expression of the form for all, which has an argument, which is an abstraction, okay? So I will be able to rewrite using this rule, even if I have for all B something, okay? Because the matching will be done modulo alpha. And as you can see, these are just plain rewriting rules. They rewrite trees, okay? I take a tree and I rewrite it. The only thing different from what a first-order rewrite language or Prolog would do is that it's modulo alpha. You can define the lambda calculus if you want, because in this system it's not part of the meta-language. So if you're interested in the lambda calculus, you need to define it. And to define the lambda calculus, you will need to define the substitution of a name for a term. And then there, you see that in higher order rewriting systems, for example, the beta rule is just one rule because it profits from the framework having already substitution defined in it. But our first order systems, nominal systems, the substitution they have is the first order one, so it's not enough to implement the lambda calculus. So we add this. So you can see this as a kind of explicit substitution version of the lambda calculus, except that the explicit substitution rules are just rewrite rules that take advantage of the fact that we have a system that can work modulo alpha. So we don't need to encode with indices or that sort of thing. Okay? Yes?
Normally, this is the place where you need to define alpha conversion. And there is none. I mean, normally you need to check that the y is not an abstraction when you do the substitution.
Okay, so the place where you check that there is no capture is when you move the substitution under a lambda. So that's the sigma lambda rule there, okay? This one. This one moves the substitution for A under the lambda. And it has a condition. Okay, so it moves the substitution. Yeah, okay. So it moves the substitution provided that B is fresh for Y, so it's not going to be captured. Okay, so that's where you see it doesn't do capture.
But what if it isn't?
Well, it doesn't really matter because, so I need to go back to the axioms and perhaps emphasize that we are with this nominal set semantics, with the axiomatization we have, the names don't have any particular meaning in themselves. So all names are represented just by a name. That's why we call them sometimes atoms, because they don't have structure. And these axioms, which sometimes are called equivariant axioms, tell you, in particular, look at the one on P. So if a predicate holds for X, you have the right to swap names in X, and it needs to work too. So you cannot, predicates are equivariant. The nominal relation is equivariant, which means that when we generate rewrite steps, I should have emphasized this better. When we generate rewrite steps, so because this is done modulo alpha, we can use any variant of this rule for any names. So if I put this sigma lambda in my system with A and B don't have any privileges in my system, okay? They are just two atoms. So if this works for A and B, it works for C and A. So if you happen to rewrite a term that has B inside Y, just take the variant of the rule that uses C, right? So that's why it makes it so easy to define, for example, the explicit substitution for the lambda calculus, because you don't need to, in a system like using the Brand, you would need to have the shifts and lifts and all that, but here you don't. So that is the part that is in the framework, okay? Just the alpha part. So the interesting thing is that because we kind of keep quite low down in the abstraction hierarchy, we are kind of first order plus these permutations. There are efficient algorithms. So I don't know if you recall this, but for first order terms, like in Prolog, for example, the unification algorithm is linear. There are two very efficient ones, one by Martelli and Montanari, one that uses graph by Peterson and Wegman. So those very efficient algorithms can be also used to check equivalence and unify terms modulo alpha. So in that sense, we are in a little bit better situation than if we had moved really far with a higher order framework, which makes things easy. So in a higher order framework, you wouldn't have needed the sigma rules for the lambda calculus. But the price to pay is that you then have to be careful when you're manipulating your expressions. So how do you build an algorithm for checking alpha equivalence or making unification? You just turn the rules I gave you into simplification rules. So this is the idea of Martelli-Montanari's unification algorithm. I don't know if you recall that from at some point studying the unification algorithm for Prolog, maybe. Martelli and Montanari work with multi-sets of expressions, multi-sets of equations. So we do the same thing here. We work with multi-sets of problems, and then apply simplification rules depending on the shape of our equation. So some of these simplification rules just eliminate equations, others decompose equations, etc. The interesting ones are the ones at the bottom that tell you if you have two abstractions with different names, that's where the decomposition needs to do a swapping and check for the freshness. Okay. So, and obviously you need also the rules to simplify freshness, because you generate freshness. For example, the rule for abstraction with A and B generates A fresh for L. So your algorithm then needs to simplify the A fresh for L using the simplification rules there. So this is to check equivalence. If you want to unify, you need also instantiation rules, okay? But this is enough for checking equivalence. So you might want something more than checking equivalence. You might want to find a substitution that makes two terms equal. In this context, it will be a substitution with a freshness context, okay? Or you might simply want to match things. When you match, you only instantiate the variables in one of the terms. The other one is supposed to be ground, or you consider you don't care if it has variables, you can't instantiate those. So matching is what you use in functional programming or to generate a rewriting relation. Unification is what you would use in a logic programming language. So these are just a couple of examples. So if you want to unify lambda AX with lambda BB, because we are unifying modulo alpha, the solution the algorithm would give you is that you need to instantiate X with A, and you don't need any freshness context, okay? But if you wanted to unify lambda AX with lambda BX, then the algorithm would tell you that you don't need a substitution, it's the identity, but you do need some freshness assumptions, okay? So these are the solutions that the simplification algorithm would give you. So nominal matching is decidable. You have one most general solution, and that's really good because if we are going to use matching to generate a rewriting relation, it's good that we have that. Regarding complexity, so it's almost as good as in the ground case. It's actually as good as in the ground case, in the first order case, if you have ground expressions. So suppose you have terms in the lambda calculus or terms in a process calculus and you want to check equivalences, just modulo alpha. So if your expressions are both ground, the checks have the same complexity as first order unification or matching or check. But if you are working with, for example, matching a term where you want to instantiate the variables on the left-hand side with a term that has itself variables, but you need to consider them like frozen variables, okay? That increases the complexity, it's log linear. And finally, if you really want the case where you have non-ground, non-linear expressions, it can go up to quadratic complexity. That's for matching or just alpha-equivalence check. When you do unification, things become more complicated, and we couldn't define an algorithm that is linear, okay? So for matching and alpha-equivalence, we can mimic the first order complexity. But for unification, the first order unification algorithm is linear, and we couldn't get that. However, there is a linear unification algorithm for Miller's patterns, higher order patterns, which correspond to nominal terms. So the question was, why is there this linear algorithm for higher order patterns and ours is quadratic? But I think the issue is you measure with respect to the syntax, to the size of the input, and the inputs in the nominal case are quite compact. You see, they are like first order terms. So if you have an X, you just have X, whereas in the higher order pattern, you would have X applied to A1, A2, A3, AN. So the syntax, the correspondence between the syntax of an expression in nominal terms and the equivalent in a pattern has an explosion in size, okay? So maybe that is what explains why the pattern unification is linear on the size of the input, but we couldn't get it better than quadratic. However, if you translate our problem into the pattern problem, our size n can become sine n squared, okay? But it's a conjecture, and we haven't yet found the proof for this. So it's still an open problem. So we have algorithms for this. We have formalizations both in Coq and PBS that have been done by students in Brasilia. Okay, so this is what I was telling you before, that the equations the rules are defined modulo permutative renamings. This is what people call equivariance. This I already mentioned. So nominal matching is what I was describing before. That's matching modulo alpha. That is the one I was talking about with the complexity. Now, if you want the equivariant problem, so if you are not just checking if two expressions are matchable with a freshness context and substitution, but you also want to know whether there is a variant of the expression modulo permutations that can match, that's the equivariant matching problem. It's also decidable. However, that is exponential, okay? But luckily, it's not a problem that comes up normally. So we proved that what we call closed nominal rules, the ones that don't have free atoms appearing in the expressions, in the terms, if you have closed nominal rules, then alpha is sufficient to get you all the variants. You don't need to also try to make variants by using permutations. So with closed nominal rules, nominal matching is sufficient, and that's the one that has the really good complexity. We also proved that closed rules are sufficient to encode higher order rewriting systems. Higher order rewriting systems normally impose also this way of writing your terms that doesn't allow to have free names. You can have free variables, but not free names. So all the examples I gave you before are closed, therefore you can do nominal matching in an efficient way, which is why there are some languages that already have been defined using this, and there are packages for, in particular, the one for Isabel developed by Christian Urban is quite popular. It was used, so the nominal package in Isabel was used by Larry Paulson to formalize Gödel's theorems, and he says in his paper that he really used extensively the properties of nominal terms. So, but what happens then with rewriting-based languages? So this is what triggered our interest in looking at alpha-equivalence modulo axioms. So the issue is that usually not all constructors are free. So if you want to, for example, specify the pi calculus, you need to say not just that the nu is a binder and you need alpha, you also need to say that the parallel composition is associative and commutative. The sum is associative and commutative. So you need to work with, if you're interested in unification or rewriting, you need to work modulo all these axioms. So the question is, do these combine well with alpha? Is it still decidable, efficient, etc.? So we looked, because in particular, as I said, we are interested in specifying first-order logic and process calcula that have AC operators as well as binders. We looked at combining the unification modulo alpha, nominal unification, with unification modulo axioms, which has been studied for a long time. It's called E-unification. If you don't put any restrictions on the theory, E isn't undecidable. So there are equational theories for which you can't define. It's not surprising. It links with Hilbert's 10th problem. So it's undecidable in general. But for the cases that are more interesting for us, like commutativity and associativity and commutativity, there are unification algorithms. These cases are decidable. So we did look at unification modulo alpha and E, and if E can be defined by a rewrite system, you can implement nominal rewriting as a way of finding the unifiers. But the question now is, how about C and AC, which are the cases where you don't really need narrowing in first-order syntax? You can apply standard algorithms. Can you apply those if you also have binders? So you can. So the conclusion was that you can do it, but there are some surprises. So what does it mean that you are unifying modulo C, modulo commutativity? It means that when you apply your simplification rules, in particular the decomposition rule, you know, when you have f of s equal f of t and you say s equal t, if your root symbol is or, you can decompose and unify the first argument with the first, but you could also unify the first argument with the second, which is what we are doing there in that or, in that unification problem. We unify the first argument on the left with the second on the right, and then we are left with this equation on P, which we can solve provided that ABX is equal to X. Now, in the syntactic case, that's easy to solve. You just need A and B to be fresh for X. But when you have a commutative operation, you could have an equality even if A and B are in X. For example, you could have A plus B or A or B, okay? And there A and B are free, so they are not fresh, but the swapping of A and B in A plus B gives you B plus A, which is equal, okay? So you have a solution. Indeed, you have infinite solutions for this equation. The problem here is no longer finitary. So in syntactic unification, syntactic modulo C, it's finitary. You don't have one most general solution, but you have a finite complete set of unifiers. For alpha, it is unitary, but the mixture of the two give you a zero-ary unification problem. It's not even infinitary. It's not that you have an infinite complete set of solutions. It's that there is no infinite complete set of solutions. There is no complete set. You just have to enumerate infinite unifiers, which is not great, but then this is all relative, because the classes of the unification theories depend on the way you want to express the solution. So these classes are unitary or finitary or whatever, because we are expressing the solutions in a particular way. Here, we want to express the solutions with a substitution and a freshness context. In the syntactic case, it's just a substitution. What if we find another way of expressing the solution? And that gives the clue to what the good way of expressing the solution is, which is, instead of a freshness context and a substitution, we allow also what we call fixed point constraints. Because that equation there, what it's telling us is that x is a fixed point of the permutation AB. Okay? So if you do allow that, then that's your solution already. So the problem is no longer zero-ary with that representation. So we did do that. We have a paper where we explain how to translate from freshness to fixed point constraints and get a finitary algorithm. And that problem doesn't happen if you're only interested in matching. So nominal matching, nominal C matching is finitary. For C unification, as I say, if you insist on using just substitution and freshness, then you will have to put up with these infinite unifiers. But if you are happy to use fixed point constraints as part of the solution, then it is finitary. Okay? So that's for C. For AC, things are complicated again. AC matching, it works. So AC unification in the syntactic case boils down to solving the Diophantine equations. I don't know if you're familiar, if you've ever seen Stickel's AC unification algorithm. It's one of the most popular ones. It's well known that to solve an AC unification problem, you need to solve a Diophantine set of equations, which it's normally in the decidable class. So AC unification is decidable. But the problem with the nominal AC unification matching is that, again, there is an interference. We believe it is decidable, and it would be also finitary, probably, using these fixed point constraints, but that's still work in progress. And it's work in progress that we need because we are interested in extending mod with nominal features, so that mod, which is a first-order rewrite language, can easily express languages with binders. But mod uses AC operators routinely, so it's good that we have AC matching and AC unification. As I say, nominal AC matching works well. We have a formalized algorithm in PVS. For unification, still to do. Okay, so I'm going to finish with this summary. You see, when I was telling you at the beginning that I really like PPDP and LOPSTR, many of these works with results I mentioned were presented in PPDP and LOPSTR, some almost 20 years ago, nominal rewriting. The nominal unification, the quadratic lower bound was in 2010. Sorry, quadratic complexity, an algorithm of quadratic complexity for nominal unification was presented in LOPSTR, but we don't know the lower bound. That's a conjecture I mentioned before. We have some work that I didn't mention on adding types to these systems, and some extensions. Nominal C unification was also presented in LOPSTR. First, the decidability, then the algorithm that enumerates the infinite solutions. And last year, we defined matching logic with nominal features. Matching logic is the basis of K, the verification, programming language verification framework K. So we added nominal features there, and still working on the extension of rewriting logic with AC. There are implementations of the algorithms I mentioned. There are some libraries, nominal libraries, one for Haskell, implemented by Jamie Gabai. If you go to the nominal project of the University Brasilia, you can find the formalizations in PBS and some in Coq of the algorithms, alpha-equivalence check, matching, unification, also modulo C, and also matching modulo AC. If you're interested in nominal versions of Prolog, I would recommend looking at James Cheney's website. James and Christian implemented a version of Prolog with nominal features. It's called Alpha Prolog, and there's also a model checker attached to it. I also mentioned nominal Isabel, which you can find, again, if you go to the Isabel page. And I think that's all. Thank you.
Questions?
Hi, do you know what the situation is for theories, I don't know what you call them, where variables can disappear, where you have like inverses, say Boolean rings or Abelian groups?
So we are, at the moment, still trying to solve the problem with AC, okay? So what the solutions we have right now are, if you have a theory, like for Boolean rings, I think you can define a theory which is a representation which is based on a set of confluent and terminating rules. In that case, you could apply narrowing. We have nominal narrowing, and under certain conditions, it even terminates. So Santiago was working on, for example, finite variant narrowing, versions of narrowing that can make things easier. So at the moment, if you have binders and operators that satisfy the equations of a Boolean ring, the only solution I could say is try to use narrowing. But we are working on AC, and hopefully after AC, we will go to AC and unit and do a bit more. Okay.
Yeah, hello, thank you. Very informative, interesting talk. I've just got a comment, and I'm not really sure whether it's relevant in the context of the aims of your work. But if the complexity of unification is linear in the size of the terms being unified, in the context of a computation, the size of terms may grow unbounded, which is, of course, why Prolog has, by default, not implemented the occurs check, because you want unification to be more or less constant time, or depending only on the size of the rules or the program that you put in. So do you envisage that if nominal logic is used as the basis for a programming language, a practical computing system or proof system, that you would need to have something similar to dropping the occurs check?
Yeah, if you want it to be almost constant, like you say, yes. The algorithm is very, very similar to the first order one, because the extra complexity, which is these permutations, basically, you can deal with it with a good data structure to represent the permutations. So you need to be able to quickly find the image of a name, the inverse, and compose these permutations. So we have a good way of doing that. And the rest is just, you need the same ways of avoiding the explosion in size. So we have the same kind of data structure as you would use in a first order language, the same problem with the occurs check. So I think in that sense, it should be similar, which is why the alpha Prolog works like Prolog. Mm-hmm. You don't really see a difference.
Yeah, it's often seen as a criticism of Prolog that
Yeah, well, it shares, the nominal prologue shares the same advantages, the same criticisms, yeah.
Here.
Thank you. Oh, this is only a technical question. I'm not an expert of the field. So when you design the algorithm, the unification algorithm, I have in mind, for example, the Milner algorithm for ML types. Well, what you do is, in that case, what you do is to generate a set of equations, and then eventually when you have the whole set produced, then you try unification and so on. In this case, you have something more because you have the freshness condition. So probably you generate not just equations, but sequence somehow. So how do you, my question is simply, how do you keep track of this essential constraint? Without it, it will be perfectly unsound, anything.
It's an excellent question. So when you are applying your simplification rules in the unification algorithm, avoiding explosion of things using pointers, etc., like you would use in Patterson's or with the Martelli-Montanari with the multi-equations, etc., you will generate these freshness constraints. So to keep the complexity down, you need to make sure you do several things. First, have a very good data structure to represent these permutations. Second, I told you permutations suspend on variables when I said that. In the algorithm, they suspend also on the top of the term. They are lazy. So you don't apply the permutation all the way and suspend on the variable. You suspend it on the top of the term and only apply this permutation if you really need it at the end. Okay? Because otherwise, each time you have a permutation, you have to traverse the term to the variable leaves. We don't do that. We treat permutations in a kind of lazy way. We accumulate all the freshness constraints. In fact, what we accumulate is for each variable the list of atoms that need to be fresh. And at the very end, we do all these tests at once. So, yeah. So the algorithm is not trivial. It's Christophe Calvet's thesis. He did both the Martelli-Montanari version and the one with graphs for the nominal terms, okay? And he also was the one that proved the complexity of the matching. So that table I showed you is all part of Christophe's thesis.
Any more questions? Well, I have... we can talk later. And we have talked several times. So, I mean, just to say that as an expert in mod, as an expert in unification, and also as an expert in cybersecurity protocol analysis, so I think that it is very important that you continue, okay? And there are many possibilities, okay? And as we, yes. And I will have this coming many times. So I mean, all these advances that you keep doing, okay, are essential because indeed, I mean, these bindings are everywhere, as you showed at the beginning. Okay, so
thank you so much.
You're welcome.
Thanks.
So let's end, Maribel.